Hello everyone, welcome to my YouTube channel. My name is Dr. Subhasis Das, working as an associate professor in the Department of Electronics and Communication Engineering, SR University, Warangal. This is my YouTube channel. Please do like, share, and subscribe. Here I will be posting different electronics engineering related videos to understand the basic undergraduate courses very easily. Today we will discuss about the p-n junction and its formation and the equilibrium conditions. Okay, let's start. So first we will see what is a p-n junction. Okay, so here you can see that a p-n junction is formed by joining a p-type semiconductor. Obviously p-type means it will be rich in holes with an n-type semiconductor which will be rich in electrons. Here region means this is the majority carriers, holes are the majority carriers and electrons are the majority carriers here in the n type. Okay, so here is the image of a p-n junction. You can think of p side. So this side, this region is p side and this side is n side, and you can easily see that. Okay, so you might be wondering that we are saying that the p-type is enriched or the majority carrier are the holes, but here it is showing electrons. So basically, so these are immobile ions. Okay, so here because you might be heard about Na and Nd. Okay, so Nd. So this side, so this is the Na plus and this side is Nd minus. So basically, sorry, it will be Nd plus donor. Okay, Nd plus and Na minus. Okay, now we'll see the p type is the doped with acceptors. Okay, and holes are the majority carriers. That's why we see these acceptors. Okay, and here this side we see is donors in the n side. Okay, as expected, the on side, the n side has the donor, so the majority carriers are the electrons in this side. Okay, now when joined, carriers diffuse across the junction, initiating equilibrium process. Okay, so when these two sides are joined together, okay, so what will happen? Because this p side we have lots of holes, n side we have lots of electrons. So essentially, what we see that for the p side, this side is less holes. Okay, so the holes will see a gradient this way from left to right, whereas the electrons will see a gradient opposite way from right side to left side, that is from n to p. And as we know, the diffusion depends on the concentration gradient. So for the holes there is a huge concentration gradient from left to right, and for the electrons there is a huge concentration gradient from right side to left side, and that makes the diffusion process to start. Okay, now you can see due to diffusion, electrons and holes diffuse around randomly. Okay, now we will see what is diffusion. Okay, so diffusion is basically the movement of carriers from high to low concentration regions. This is very simple. And on the other hand, another process you will see these things also, that is called drift. Okay, so movement due to electric field opposing diffusion. Okay, so the basic difference between drift and diffusion is that diffusion starts automatically whenever it finds any concentration gradient, but for the drift process to start we need to apply some electric field. And here in this case we will see that this electric field will oppose the diffusion process. Okay, so there is a clear distinction between the diffusion and drift process. Okay, now electrons diffuse from N to P, holes diffuse from P to N. These things we already explained in the previous slide. Okay, and this creates a depletion region, a zone devoid of free carriers. Here we will see that here it creates a depletion region. So this region is devoid of free carriers because of this equilibrium process and this transfer of the electrons and holes, or rather we should say that the diffusion of electrons and holes to the other sides, we will see a depletion region created. Why it is saying the depletion region? Because this region is depleted of any charge carriers. So there is no free charge carriers in this region, and it will be created at the junction of P and N. Okay, so an internal electric field forms opposing further diffusion, and because of this pile up of this charge carriers near this region, we will see that an internal electric field pile up. Okay, so this side is this negative, negative, this negative, this negative, this negative, and this side is this positive, this positive, this positive, this positive. And because of this positive and negative immobile charge piled up at the junction, we will see that an internal electric field is formed. And finally, we will see this, that this internal electric field will oppose the diffusion process, right? Now we will see the depletion region and the built-in potential. Okay, so that image is saying that this region is the depletion region, right? This is depleted of any free charge carrier. That's why we are calling this as the depletion region, sometimes called as the space charge region. So when the materials are joined, carriers cross into the other region. That is obvious for the diffusion. Okay, and however, the fixed ion cores that are left behind set up an electric field. So what are the fixed ion cores means? Here this side is negative ions, this side is negative ions, and this side is positive. This side is positive ions, right? So the depletion region, what is depletion region? Area near the junction where mobile carriers are depleted. That's what we are saying, that this is depleted of any charge carriers. Right. Now what is built-in potential? Okay, now we'll try to understand another important factor for PN junction. What is the built-in potential? So the internal voltage developed due to carrier diffusion. Okay. So due to this carrier diffusion, the internal electric field is built up, and because of that, a potential is also built up. Okay, because we know E is equal to V by D. D is the width. Okay. So the immobile ions remain after carrier diffusion, creating space charge. Okay. So the immobile ions remain after carrier diffusion, creating space charges, and that's what I am saying. Okay. Electric field builds up, leading to band bending. Electric field builds up, and finally it gives us the band bending phenomenon. And then Fermi levels align across the junction at equilibrium. If you see the if you see that, okay, sorry, so we can see this thing very easily. So this band bending, this Fermi level will be in equilibrium. So the basic of this band diagram is that the Fermi level should be equivalent or throughout the same when the junction is formed. So Fermi level is not bent here, it is throughout the same at the equilibrium. We are talking at the equilibrium condition, right? Now the electric field tends to keep the holes in the p-type material and the electrons in the n-type material. However, even at thermal equilibrium, some carriers have sufficient energy to cross the depletion region. Okay, so this is the built-in potential. What are the key equations? Where we will see the Poisson's equation governs the electric field and potential, and the depletion width is equal to Wn plus Wp. So Wn is the depletion width at the n side, and Wp is the depletion width at the p side. And here is one important formula which will be used often, that Vbi, the built-in potential, is equal to Kt by Q ln NaNd by Ni square. Now we will see what are these terms. So NaNd, as I described earlier, this is the acceptor concentration, this is the donor concentration. Okay. Ni is the intrinsic carrier concentration. Okay. Okay. So this is the intrinsic carrier concentration. Kt by Q is the thermal voltage. Okay, where K is the Boltzmann constant, T is the temperature at absolute the temperature in Kelvin, and small q is the electronic charge. So these equations describe the electrostatics of the junction. Okay, so we will see here that zero voltage across the diode, no current flows at equilibrium. Okay, so what we'll see that moderate electric field in this direction, because here this side is negative charge piled up, this side is positive charge piled up. So the electric field direction will be from n side to p side, and because of this direction of the electric field, further p side to this side will be restricted. So that's why the internal electric field actually opposes the diffusion. Okay. Equilibrium occurs when the drift and the diffusion currents balance, resulting in zero net current. Okay, so because of this electric field, okay, so there will be two phenomena as we described, the diffusion. So diffusion current will be diffusion of holes from here to here will give some current. Diffusion of electrons from here to here will give some current. And for the electric field, there will be some drift current. Okay, so the drift current will also be there due to this electric field. Okay, so the whole drift current will be this way, and electron drift current will be this way. Okay, so no external bias is applied, right, at this condition, because there is net zero current, and that's why we are saying this condition as the equilibrium condition. And the internal electric field exactly cancels the diffusion forces, right? Carrier concentration stabilizes, of course, that's why the equilibrium is established. So these are the different things. Now we will see some applications of PN junction. That diode, we very often use diode. Solar cells, diodes, LEDs, laser, light emitting diodes, transistors. Okay, in transistors also we use in the NPN or PNP also. There are PN junction, NP junction. Here is also PN junction, NP junction. So PN junction is also used in the transistor. So these are the suggested question for PN junction. The what happens to the electrons in the n-type region during PN junction formation? What is the primary role of the depletion region in PN junction? What causes the built-in potential in a PN junction? Which type of charge carriers dominate in the p-type region of a PN junction? What is the equilibrium condition in a PN junction? What is the role of the electric field in the depletion regions? So all these questions we have already discussed. So these could be the possible questions from this PN junction formation and the equilibrium. Okay. So now, so far whatever we discussed, if we can summarize, so that the PN junction formation, a PN junction is formed by joining p-type and n-type semiconductors, enabling rectifying behavior essential for diode. Next point what we understood, that the carrier diffusion and drift. Electrons and holes move across the junction due to concentration differences, that is called diffusion, and electric field, that is called drift. Another point which we learned is that the depletion region and the built-in potential. So the junction forms a depletion region void of free charge carriers and creating a built-in potential that opposes further carrier movement. Okay. The fourth point what we understood, the equilibrium and the applications. So at equilibrium, diffusion and drift currents balances. So diffusion and drift currents for both electron and holes balances each other. So there is net zero current at the equilibrium condition. And the PN junctions are widely used in diodes, solar cells, and sensors. So these are the key summary points of the understanding from PN junction diode and equilibrium formation. Okay. Now we will see the forward bias and the reverse bias conditions of the PN junction diode. Okay. Now, before going to the forward bias and reverse bias, we will see what is biasing. Okay. So biasing refers to applying an external electric voltage across PN junction to control its behavior. So far we have discussed the built-in potential, which is the result of the internal electric field as developed by the pile up of immobile charge carriers near the junction. Okay, but here we will see that we will connect external voltage or power supply to control the behavior of the PN junction. Okay, so what are the types of biasing? So biasing can be categorized as forward bias and reverse bias. Okay, so forward bias is this side is P side, right? This side is P side, this side is N side. So P side is connected to positive of the battery and N side is connected to the negative of the battery. And this condition we call this as the forward bias condition. And the reverse bias condition obviously will be the opposite, where the P side is connected to the negative part and N side is connected to the positive part. Okay, and this condition or this biasing condition we are calling it as the reverse bias condition. Okay, so there could be two different types of biasing possible, forward and reverse. Okay, now we will see what happens. So this is the previous diagram. We have already noticed the different current conditions for electron, hole, and their diffusion and drift current. Okay, so now here I hope you understood that this is the positive side and this is connected to P side. That means this is forward bias, right? This is forward bias. Okay. So now in forward bias, the external voltage reduces the potential barrier allowing current to flow. So in the forward bias condition, what it does, actually it reduces, suppose this is the barrier, right, at the equilibrium condition. But after the forward bias, this barrier will be reduced to this. Okay, so that means it has reduced. So that is the purpose of applying the forward bias, that it reduces the potential barrier, thus allowing further current to flow. Explanation, what is the explanation why it is happening? So the depletion region narrows, okay, and the majority carriers move toward the junction. Because the depletion region is shortened, so the more majority carriers are near to the junction, and that current flows once the voltage exceeds the threshold voltage 0.7 volt for silicon and 0.3 volt for germanium. So this voltage is sometimes called the cutting voltage of the diode. Okay. Next we will going to see the IV characteristics of this diode in different biasing condition. There we will see this 0.7 volt, and we will find that that is the threshold volt. After that, actually the current starts flowing very heavily. Okay. So now forward bias energy and band diagram we will try to understand. Okay. So when isolated, so this is P side, right? This is N side. So when isolated, as you can see, the Fermi energy lies, this is the Fermi energy lies near to the valence band. And for the N side, this Fermi energy lies near to the conduction band. So that is the basic of the P and N type band diagram. Okay. And when connected, so as I have shown that this Fermi level will be same throughout the material, throughout the P and N both junctions, so that this band is bent to accommodate all these uh, uh, different in the energy in N side and P side, and this gap is termed as the EVBI. EVBI, what is VBI? VBI is the built-in potential. So how much will be the barrier? That will be decided by the built-in potential itself. Okay. Now this side we can see that this is the forward biasing, right? So positive side is connected to P side, and as you can see that this band bending is has become less because of this forward bias, so that the barrier has been reduced for the electrons to go from here to here. Okay, so this forward bias actually helps more electron to go to the other side and thus creating the more current. Okay, if you see the concentration of carriers, you can see easily that how it changes for both the sides. Okay, and the current density also changes. So this is the explanation with respect to the band diagram. Okay, now so this is the band bends downwards. That is the explanation. Fermi level shift due to applied voltage. Okay, and electrons from N side and holes from P side overcome the barrier because of this lowering of the barrier due to forward bias. Now we will see the forward bias IP characteristics. So this is the standard equation for the diode. So ID is the diode current, I0 is the reverse saturation current. That we will also see after next slide or so. And this Q we already know. Q is the electronic charge, V is the diode voltage, K is the Boltzmann's current, Boltzmann's constant, T is the temperature in Kelvin. We will see all these things. So the exponential rise in current after threshold voltage. So this is the threshold voltage. As you can see here, this is the 0.7 voltage, right? Current increases very rapidly after that. Right. So before the threshold, negligible current flows, as you can understand from this curve. And after the threshold, rapid increase. Actually, this is exponential increase. Okay. So as I have already explained, we know the value Q is equal to 1.6 into 10 to the power minus 19 coulomb, and K is the Boltzmann constant whose value is 1.38 to 10 to the minus 23 joule per Kelvin, and T is the absolute temperature in Kelvin, that is 273 plus whatever the degree Celsius temperature. Okay, so this is the explanation of the forward bias diode characteristics. As you can see, this is the actual commercially available units. Theoretically it might be showing so much state, but actually available commercial diodes have this kind of characteristics, little bit slower steep. Okay, and this is the knee voltage. After that it started very heavily. Okay, now we'll see the reverse bias condition. Actually the things will be opposite in the case of reverse bias, because in the forward bias actually the biasing help in increasing the current, and in the reverse bias it will oppose. Okay, so as you can see, this p side is now connected to the negative side, negative side is connected to p side, that means this is reverse bias, and we will see that the depletion region actually widens for this kind of condition. So in the reverse bias, the external voltage increases the potential barrier, preventing current flow. If the potential barrier is increased further, so less amount of electrons or holes can cross the barrier. That means current will be reduced. Okay, actually it is opposing, and the depletion region widens as I explained earlier, and the majority carriers pulled away from the junction. That is also very obvious. You can see from the image. So tiny leakage current flows due to the minority carriers. Although the all majority carriers are being pulled away from the junctions, but still some minority carriers will be available to conduct the current, right? And that will give you some current which we will call the reverse saturation current. And now we will try to understand in the similar fashion like on the forward bias we understood, and here also we will try to understand the reverse bias like earlier also we already noticed this thing and this thing. Okay, this is common for both the case because this is the equilibrium condition, right? Now we will see what happens due to the reverse bias. As you can see, this negative is connected to p side. Okay, now you see the barrier has been increased so much. Earlier this it was like this much of amount, now it has become this much of amount. Okay, so this is really big amount, so that means this barrier height has been increased. So it it has been difficult for the electrons to overcome this much of barrier or holes to overcome this much of barrier. That means less amount of electrons or holes will cross over, and resultingly we will see less current, right? So this is the reverse bias characteristics. Very small reverse current, leakage current, actually like this. This is very small amount in the micro or nano ampere order. Okay, and at high reverse voltage breakdown occurs, that is called, one type is Zener and another type is avalanche type. We'll discuss those things later, not now. So at the very high bias it could be possible that the Zener goes into the breakdown, and the breakdowns also have two kinds of processes to follow. Another one is Zener and another is avalanche, depending on the type of the breakdown. Okay, and the breakdown leads to sudden surge in the current. Okay, so let's see if this is the axis. Okay, if your saturation voltage is going like this, if your saturation is voltage going like this, suppose this is the breakdown voltage region, and once it comes here it will suddenly start going like this, very much straight. Okay, so this point is called the breakdown voltage. Okay, now we will compare the forward and reverse bias and what are their characteristics. As far as the connection is concerned, forward bias P side to plus, N side to minus. For the reverse bias P side to negative, N side to positive. For the depletion region, For the forward bias, it narrows, and for the reverse bias, it actually widens. For the current flow, for the forward bias, current flow increases, that is high, and reverse bias, it is opposite, very low. The barrier potential actually decreases for the case of forward bias, and because of that, actually, we are seeing the high current. And this case is opposite for the reverse bias because the barrier potential increases and we see less amount of current. Okay, and the band diagram, band bend downfalls. Actually, the bending is lessened due to the forward bias, where the band bend is upward because of this reverse bias. It bends more. Okay, and the breakdown possibility in the forward bias, there is no possibility of breakdown, whereas it is very much possible for the breakdown in the reverse bias, but it could be general or avalanche in nature. Okay, so what we learned that before that we will see some applications. The forward bias is the diode, and the rectification happens LEDs, light emitting diodes, lasers, all these are forward bias application. Reverse bias is photodiode, Zener diode for voltage regulation. These are some the reverse bias applications. Okay, so what the questions could come? So here the questions could be: describe the action of PN junction diode under forward bias and reverse bias. So that the PN diode works as a rectifier. Explain how unidirectional current flow is possible in PN junction diode. Explain characteristics of PN junction diode. Indicate the differences between the characteristics of silicon and germanium diode and state approximately their cut-in voltages. The cut-in voltages are different for both type of diodes. That's why they, the reviewer or the examiner might ask these questions. Okay. So what we learned from here, the biasing in PN junction. Biasing controls the direction and the magnitude of current flow across a PN junction by applying external voltage. Okay, and what is forward bias and reverse bias? In forward bias, the depletion region narrows, allowing the current to flow easily, as shown in the energy band diagram and the IV characteristics. And on the other hand, in reverse bias, the depletion region widens, restricting the current flow, and except for a small leakage current until the breakdown occurs. Applications: biasing principles are used in rectifiers, switches, voltage regulator, and various other electronic applications. So that's it what we understood from the course. I hope that the students are now able to describe the concept of biasing and PN junctions, analyze energy band diagrams and IV characteristics under forward and reverse bias conditions, and explain their applications in electronic devices. Thank you for watching this video. We'll see you in the next video. Thank you for watching.